Okay, we're continuing on here, chapter 13. We were talking about acids and bases last time. To remember that an acid is really something that can produce H plus ions free in solution. And again, remember that when we're talking about acid-base chemistry, H plus, H3O plus, they are basically equivalent to each other. So again, H plus is the hydronium ion, or H plus is the hydrogen ion. H3O plus is the hydronium ion. And they're used interchangeably, as we talked about last time, in equations, also reactions as well. Bases are things that have the ability really to produce hydroxide ions in solution. And remember that what we're talking about really here is the ability to have these guys sort of freely floating in solution, not really obviously attached to anything and so forth. And as we'll talk about, obviously, the amount that you have of, say, free H plus versus free OH minus will determine, again, whether or not a solution is acidic, basic, or neutral. We talked about a more generic definition of an acid and a base, and one that people oftentimes talk about, which is the Bronsted Lowry definition, where an acid is a proton donor and a base is a proton acceptor. A reminder that sort of the consequence of the Bronsted Lowry definition of an acid and base is it will create partners. So, for example, we have this that I think we might have saw last time. This is going to be our acid, which means it's going to send the H plus over to the water in this case, which is acting as the base. It will then create a partner on the other side, which is known as the conjugate base, while the water, which will accept the H plus, will create on the other side what is known as the conjugate acid. So once again, kind of your regular acid and base on the left-hand side of the arrow, your conjugate pairs there on the right-hand side of the arrow. And again, the only difference, as we talked about, I think at the very end last time, that there can be between these two things in order for them to be pairs is just one H plus. So if it's any difference greater than one H plus, then they are not going to be partners. They are not related to each other in that sense. Cool, thank you. Any questions on any of that stuff there we talked about last time? All right, then I think we did that one. So I think here. So I think we're on this one here. So why don't you take a moment and for each of these, decide whether or not they are acid conjugate base pairs. Okay, so let's take a look at these. So again, the deal is we're really looking for a difference of only one H plus. So when we look at the first one here, we have HCl and OCl minus. The difference here is one H plus, but it is also a oxygen, right? So because of that, they are not pairs. So again, it cannot be anything more than one H plus difference. H2SO4 and SO4 2 minus, are they pairs? They are not pairs either, because the difference between these two things is more than one H plus, although they are related to each other, obviously, but they're definitely not pairs in this case. We're going to go with NH4 plus and NH3. Difference between these two guys is, yeah, only one H plus. So there we found somebody. And again, you can see that by either putting the H plus on the NH3 and you get NH4 plus, or you take away the H plus from the NH4. So that looks like a winner. H3O plus and OH minus, again, here is more than one H plus, so that would not be one. And I'm assuming none would not be one either. So again, that has to be the only difference. Now, You might be wondering, SO4 2 minus, for example, and H2SO4, they do seem related to each other. And you're not wrong in the sense that they are related to each other, but they do not meet the definition of a Bronsted Lowry acid or base conjugate pair. And that is because H pluses actually do come off one at a time. So when we lose H pluses, they don't both come off. Something like H2SO4, which is, as they like to call it, a diprotic acid. Yeah. It's a diprotic acid because it has the ability to lose two hydrogens in this case. A reminder that an acid, right, the cation is always the H plus, and in this case, it can lose two. What happens here is actually the first one will come off, and you'll make something like HSO4 minus and an H plus. Then that HSO4 minus will then lose another H plus and make SO4 2 minus in this case. So it actually comes off in a sort of a stepwise fashion. It is not both of them coming off at once. Is it easier to remove the first hydrogen or the second one? Which one's easier? The first one is much, much easier. When you remove the first one, you now have something that has a negative charge overall, right? And you're trying to remove something that's positive. So it makes it a little bit more difficult to pull that off. And it does get a lot less coming off. That is why when we look at pairs, for example, this guy and this guy, those are pairs. The only difference there is one H plus. This guy here and this guy is also a pair, as again, the difference there is only one H plus between them. As we try to jump again, like in the question here, from here to here, they are not pairs because again, it's obviously two H's gone at that point. So diprotic acids, which have two hydrogens to come off, they do come off one at a time. Triprotic acids, which have three hydrogens to come off, they come off one at a time as well. Gets much, much harder when you try to rip off that third hydrogen versus the second. Good luck with that. Not very much is going to come off at all. But it definitely is a stepwise sort of dissociation, sometimes referred to. Any questions on that there? All right, let's try another one here. We got C6H5NH2. What is the conjugate acid for this one? I imagine the right answer might be up there, hopefully. All right, so if you're not sure, and sometimes they obviously will not give you multiple choice there of what to choose from, and they oftentimes will not tell you what things are. The relationship of the Bronsted Lowry that we talked about is really important to think about. Again, we have an acid on the left there, a base on the left. We have a conjugate acid on the right and a conjugate base here on the right as well. So the acid on one side is related to the conjugate base on the other. The base on one side is related to the conjugate acid on the other. At this point, you should hopefully know that it's all about the H plus. But the big question is, should you put it on or should you take it off? And that's the question sometimes people have a really hard time answering. So if you understand the relationship of the Bronsted Lowry sort of acid conjugate base pairs, when we were asked to write the formula of the conjugate acid, if we just follow it backwards, that means, again, what we are staring at are bases. And you can just go by the definition of the Bronsted Lowry base, which is it should accept an H plus. So that will tell you that you should put the H plus on. So everything stays the same, except that you're going to stick an H plus there at the end. So we're going to add one more. And remember, it's not just the H, but it's also the plus. And that looks like maybe number 2. Looks like a winner there in that case. Question on that. Now, let's say we had something like HCO3 minus. Why don't you write the formula for the conjugate acid and also the conjugate base. So starting with a little bicarbonate in each case, write the formula. Okay, so let's take a look. Once again, what we'll start here on the right. We're going to go with the conjugate base first. So if you're not sure, we know that the conjugate base is over here. That's where we want to end up. So if we kind of work our way backwards, we know in this particular case is going to act as an acid, which means the definition of an acid is it should donate the H plus. So we should have one less H plus, which if we get rid of the H, we're left with CO3. We lose the plus, which means we become one more minus, and that will be carbonate in this particular case. Question on that one there. Now our conjugate acid will be just like the question here. Conjugate acid means if we go backwards, once again, this is in this case going to act as a base, which means it's going to accept the H plus, and it should end up with two hydrogens, a CO3, and a +1, and -1 will give you 0 for the charge, and you'll end up with a little carbonic acid, which is where this goes from. Question on that. So you want to think about it sort of backwards sometimes if you're not sure, because a lot of questions they won't tell you, hey, these are acids, these are bases. They'll just ask you to write either the conjugate acid or conjugate base for what you got going there. So if you know that's where you need to end up, just think about what is the partner on the original side. And then really at that point, all you have to do is just use the basic definition of Bronsted Lowry in terms of an acid or a base. Any questions on that? Yeah. Yeah, so the conjugate acid is always related to the base, which means if that's what you're starting, which would be the base, it should accept not just an H, but the plus part too. So the H plus onto it. And the opposite would be true for the conjugate base. That means it should be what you're looking at as an acid, which means you should subtract off the H plus. So, other questions? Now, this is bicarbonate, right? Which in certain cases can act as an acid or a base. Those are things which are known as being amphoteric. An amphoteric substance is something that can act as an acid or a base. And typically things with a hydrogen and a negative charge have that ability. Like the one we saw on the previous slide there, the HSO4 minus could also go both ways. It's got a hydrogen to give, and it can accept a hydrogen as well. So it's able to do that. And also our friend water, as we saw in some of these earlier slides, can go both ways. We saw water with hydrochloric acid here, where it's going to accept the H plus and again make something like H3O plus and Cl minus. We also saw it when it was with ammonia. It will actually donate the H plus over and make a little NH4 plus and OH minus. So water is another example of something that can act either as an acid or a base, depending on the sort of the situation. Any questions on that there? So speaking of water, since water can act as an acid or a base and is amphoteric, when you get a couple of waters or so together, they're going to react just like that. One's going to act as an acid, one's going to act as a base. That's pretty much what's going on with water at all times. So that is what is sometimes referred to as the autoionization of water. In one case, a water is acting as an acid, and in the other case, it's acting as a base, and it will produce H3O plus and OH minus. And that is actually an equilibrium reaction that occurs. And since it is an equilibrium reaction, we know we could write an equilibrium constant for that, which again would be our products over our reactants. In this case, it would be K times the concentration of H plus times the concentration of OH minus. Would I put that in the expression? I would not, because that is a pure liquid, right? So it would not go in the expression. This K, to add to our growing list of Ks, we have KC and KP so far. This is our friend KW to add into the mix. I'm going to go with water for W. That seems logical in this case. So KW is equal to the concentration of H plus times the concentration of OH minus. And by the way, that equals, as we will see on the next slide, 1 times 10 to the minus 14 at 25 degrees Celsius. Like any other K value, technically the KW value does change with temperature. So it can change and have a different value, but I would say probably 9 times out of 10, that is going to be the value you're going to use. Probably even more than that, maybe. Well, that will definitely be the value that you'll use in most cases. So this is what's going on in water at all times. We have H plus is floating around, OH minus is floating around. As a result, again, of just really water kind of reacting with itself. So when we look at this, which is KW, and obviously it creates our conjugate acid base pairs in this case, our acid and our conjugate base, and our base and our conjugate acid. And again, obviously in this case, both water is the acid and base on the left-hand side in this particular case. So we would have the H plus going over that away. If we look a little bit more at this KW, we get the concentration of H plus and OH minus. And this is one of the formulas here, again, that KW will equal our H plus and our OH minus. That does equal that 1 times 10 to the minus 14. You can, again, swap out the H plus for H3O plus and OH minus. So again, as I said before, I usually roll with H plus, but books and stuff will roll with H3O plus. It's the same thing. The H plus or the H3O plus is basically the acid part of the solution, and the OH minus is really the base part of the solution. It is, as I mentioned, 1 times 10 to the minus 14, so that's a number you should know, and that's a number that you should use a lot, and they oftentimes will not give you that number in a problem. They just assume that you kind of know that number and that relationship. As I mentioned a second ago, it is a K value. So as we talked about, temperature is the only thing that affects the actual value of K. So if you come across a problem, which sometimes books like to do occasionally, they sometimes like to give you problems at different temperatures, and you need to use KW, you would actually have probably a different value to use. And usually they would probably give it to you somewhere in the problem and tell you, hey, at whatever degrees to use this as for KW. Outside of that, like, it's a pretty safe bet just to use 1 times 10 to the minus 14 in most of your calculations, unless again you see something specifically they mention about temperature and that type of stuff. So what can we do with KW? We can use the concentration of H plus versus the concentration of OH minus to determine whether or not this solution will be acidic, basic, or neutral. So if you calculate and the H plus concentration, which is the acid part, is equal to the OH minus concentration, which is the base part, then you have a neutral solution. Now, if you calculate it and the H plus concentration is greater than the OH minus concentration, that means essentially your acid part is bigger than your base part, then the solution would be acidic. And if you do the opposite there and see that the OH minus is a larger value than your H plus concentration, then obviously your base part is larger than your acid part, and it would be a basic solution. So this is one way that we could calculate whether or not a solution is acidic, basic, or neutral. The good news is it's the same calculation regardless of what concentration you're given. So if you want to find the H plus concentration, you take the KW divided by the hydroxide concentration. And once again, that KW is the 1 times 10 to the minus 14 number. Or if you want to find the OH minus, it is the KW divided by the H plus concentration. Really, really important in this chapter, exponent button. Yeah, especially when you start punching these things in. Make sure you are using your exponent button correctly. Otherwise, you will find your answers off for sure as we grow through this chapter and other chapters. But definitely through this chapter for sure, make sure that you are using that EE button, that EXP button, like we talked about, I think, earlier on. Any questions on that there? So let's try. What is the concentration of hydroxide in an HCl solution who has a H plus concentration of 1.3, and determine is it acidic, basic, or neutral? So grab your calculator, make sure you know how to punch it in correctly. Alrighty, so we are looking for the OH minus concentration. We are given the hydrogen ion concentration of 1.3. So this is definitely our KW, which again is going to be equal to 1 times 10 to the minus 14. As I mentioned before, it's pretty much the same calculation regardless of which one you're looking for. You're basically going to take KW and divide it by what they gave you. So that would be our 1 times 10 to the minus 14 divided by our 1.3. So that's like a 1 exponent button, right? Negative button and 14, a little divide and a 1.3 and then equals. Yeah, all that good stuff. I'm going to try that myself, see how the calculator works. And if you do all that good stuff, you will get a hydroxide concentration of 7.7 times 10 to the minus 15, I hope. I punched it in right. Try it one more time, make sure. There it is. Question on that there. This would be acidic, basic, neutral. So we want to compare the H plus concentration to the OH minus concentration. So that's the H plus concentration. That's the OH minus. Which one's larger? It is the H plus by a lot, I would think, yeah, in this case. So this would be acidic, this solution. That would also make sense since this is a hydrochloric acid solution. So I would hope it would be acidic, right? So those are things you want to think about, right? Along the way. Question on that there. Again, if you find yourself with this part of the number good, but this part's off, it's probably the way you're punching into your calculator. So again, don't put any extra multiplication or anything like that in there. Let's try another one here. What is the OH minus in this solution? And is it acidic, basic, or neutral? If we have an H plus concentration of 1.2 times 10 to the minus 6. Okay, so we have the H plus concentration given to us of 1.2 times 10 to the minus 6. We are looking for the hydroxide concentration. So once again, this is going to be our KW. In this case, we're going to solve for hydroxide, which will give us our KW divided by our H plus, and that'll give us 1 times 10 to the minus 14 divided by 1.2 times 10 to the minus 6. So here we would do that, and you will get on your calculator there about 8.3 times 10 to the minus 9. We do need molarity here since we are solving for a concentration. If you didn't get that number and your calculator ran out of room, you got like 8 zeros and an 8 at the end, a bunch of 0.0008 at the end. And that's just because your calculator ran out of room, basically. So if you threw it in a scientific notation, you will get the 8.3 part of it. Now, I guess that eliminates these two, right? So now we want to compare the H plus concentration to the OH minus concentration. And which one is larger in this case? It is the H plus concentration, right? Is larger. A reminder that when you are comparing exponents that are negative, the negative is kind of important. The smaller negative exponent is actually the larger number because to the minus 6 means we're only going 6 places to the left and putting zeros. To the minus 9, we're going 9 places to the left and putting a lot more zeros. Is going to make it a lot smaller number when we move this guy 9 places this way and put zeros versus only moving this guy obviously 6 places that way and putting zeros. So negative exponents, smaller negative exponent is the larger number in this particular case. Question on KW here. All right, then let's talk about pH and the pH scale. The pH scale runs from 0. pH scale runs from 0 to 7 to a little 14 action there, the pH scale. From 0 to less than 7 is acidic. Above 7 to 14 is basic. And 7 really is neutral. Oh, okay. No worries. 7 on those there is neutral. 7 is sort of your starting middle point. And as you go closer to 0, it's going to get more acidic. And as you go from 7 upwards to 14, it's going to get more basic. Now, there is a few relationships that's important here. First off, we could calculate the pH like we see there before I scribble the line through it. pH is equal to minus the log of the H plus concentration. This again is another formula that you can substitute in the H3O plus. So again, basically the same thing, whichever way you want to remember it. So let's talk a little bit about calculators in this case. If you have a display calculator versus a non-display calculator, if you have a display calculator for this formula and all the other ones we're going to see here through this chapter, you basically would put it in exactly the way it's written. So if you had a display calculator, you would hit the negative button, again, not the subtract, but the negative button. You would hit the log button, and then you would put your number in probably with your exponent button. If you have a non-display calculator, you actually have to work backwards in this formula and all the others, which means you actually need to start with the number. Then you need to hit the log, and then you need to hit the negative button. If you're not sure what type of calculator you have, you could hit the log button. And if it says log, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. So that's the way you can remember it. So again, display calculator is pretty much how all the formulas are written directly. Non-display always got to kind of work their way backwards in terms of how you put it in there. So speaking of that, if we have a neutral solution, as we talked about before, the H plus concentration and the OH minus concentration will actually equal each other, which means the H plus concentration will actually equal 1 times 10 to the minus 7, which means technically speaking, you each get a pH of 7, and that is technically what neutral means. And that is what we're going to roll with in this class, which is if it's a pH of 7, it's neutral. If it's a little bit higher than 7, it's slightly basic. If it's a little lower than 7, it's slightly acidic. And if it's on 7 there, it is neutral. It needs to be super close to 7 to be considered neutral in this class. So that is what we're going to go with. I know some people go, that's kind of a grayish area, kind of above and below the 7, but technically speaking, the real definition is that they're equal concentrations, and it should actually give you a pH of 7 in that case. If our H plus concentration is larger than our H minus concentration, that means when you slap that H plus concentration into the pH one, you should get a pH that's less than 7. And if it's basic, our OH minus concentration is larger than our H plus concentration, which means you'll have a smaller concentration for H plus. And when you put that in there, you'll get actually a greater than 7 pH when you do that. The relationship, by the way, between H plus and OH minus is opposite. So as one goes up, the other goes down is the relationship between H plus and OH minus, and obviously vice versa there. As the concentration of that goes down, the OH minus goes up in that sense. When we have a small concentration of H plus, that would mean the opposite, that we have a small concentration of H plus, a larger concentration of OH minus, and that would give us a higher pH. When we have a higher concentration of H plus, the pH should go down because we have more H plus than OH minus in this case. So the opposite would be true. pH would go down as the concentration of H plus goes up in this particular case. Any questions on that there? So when we calculate pH, we want to think about significant figures. Maybe, I don't know. It's like a chemistry class, they say, I suppose. So let's talk a little bit about significant figures when we do calculate something like pH. So when we're calculating a value like pH, which by the way does not have units, it is just a number that you calculate. When we calculate pH, the number of decimal places in the pH type of value will equal the number of significant figures in the concentration value. So let's try our calculator, shall we? The H plus concentration is equal to 1.2 times 10 to the minus 5. What is the pH in this case? Why don't you give that a go and see what's happening there? So try it on your calculator, make sure you know how to punch it in. Okay, so let's see here. So pH in this case would be minus the log of 1.2 times 10 to the minus 5. Again, we want to make sure we use our exponent. By the way, the name actually tells you what you need to calculate pH. pH means you need the H plus concentration. So it tells you pretty much what you need to calculate that. Once again, depending on your calculator, which way you're going. If you got the display, you're going to hit negative log and punch that guy in with your exponent button. If you have a non-display, you're going to start with the number and then hit log and then the negative button. So I'm going to do that, a little negative logage 1.2 minus 5. And on my calculator here, it gives me 4.920818754, which is clearly too much in terms of an answer. But that is sort of what you should see on your calculator-ish. Yeah. Now, the answer should end up being what? The answer should end up being 4.92. The answer should be 4.92. This has two significant figures. Means not significant figures, but I have two decimal places in my pH value. So significant figures to decimal places. By the way, we're going to talk about going backwards. So if you're going backwards from pH to the H plus, you would go from decimal places back to significant figures. So it works the same no matter which way you're kind of going in that case. Acidic, basic, neutral, this one? It is acidic. It's less than 7, right? So it is acidic. By the way, you should always look at the pH scale when you're determining acidic, basic, and neutral. And by the way, when you're asked that question, there is only one answer. It's either acidic, basic, or neutral. It is not my favorite answers, which is it's acidic and it's basic at the same time. I've never had anybody really give me all three, which I guess is good. But I've had people give me the same solutions, both acidic and basic at the same time, which I guess might make it neutral at that point, I suppose. I don't know. It can only be one of those things. So most people have the pH scale in their head, and that's probably the number that you should probably look at to help you determine that if you calculate the pH. That's probably the best idea. Any questions on any of that there? This is the pH scale. And again, you can see some things here. We have sodium hydroxide, which is a strong base up there towards the top. 14, we have a strong acid there at the bottom. We got pure water there, a little blood and milk. Obviously some acids, some cleaning stuff, which is basic. By the way, if I take tap water out and I throw a pH meter in there, is it going to say a pH of 7? It's not. It's actually going to probably say like a pH of 5-ish or so and stuff. And that's because as it's out in the air, especially if it's been out for a while, it can pick up some carbon dioxide in the air. Carbon dioxide and H plus will make some carbonic acid, increase the amount of H plus, lower the pH in that solution. So it's not people are surprised when they go, "Oh, my water is not 7." You know, it's actually a little acidic there. And that's really the reason why. How do we measure that? Well, it looks like a classic Beckman pH meter. Yes. Local place over there, Fullerton, Brea. Beckman started. And that's where he started. He made pH meters. So pH meter is really a electrode that you stick in a solution, and frankly, it measures the amount of H plus that is floating around the solution. Really, it just measures voltage, and you to calibrate it, and you put a solution in there and go, that's a pH of 4. It has a certain voltage associated with it. You do like a pH of 7, has a voltage, and you do a pH of 10, it has a voltage, makes a little calibration curve. Then when you stick it into your solution, it goes, oh, it's got that voltage. That's that pH. So that's, in a nutshell, how a pH meter really works in a sense. But that is one way that we can measure pH. We could also use pH paper, which if you ever, if you have a pool or you've done any pool care, they got those little things you put in the water, right? It's got all different colors. You kind of match it up to all these things. And that's kind of how pH paper works. You kind of dip it in and it changes color. You try to match it up to kind of looks like between these two colors always, so not obviously quite as accurate, obviously, as a pH meter would be. We also use litmus paper, which really doesn't measure pH, but it does tell us if something is acidic or basic. When litmus paper turns red, right, as we talked about, I think in lab, it means it's acidic. And if it turns blue, it is basic litmus paper. Again, really won't tell you pH or anything like that. Now, there is a similar scale to pH, but it doesn't measure pH. It measures OH minus concentration. And that is what is known as the POH, hence the name OH. I need the OH minus concentration. And it's calculated pretty much the same deal as pH. You punch it in exactly the same way as pH. The only difference is that you're using the hydroxide concentration. The reason you might want to do that is there's a really nice relationship between pH and POH, which is if you add them together, you get a pH of 14, which ain't bad. So what that's really kind of nice is in some cases you may not have to use KW to answer a question. You could kind of calculate the POH if you're given the OH minus concentration, and then you can just subtract 14 from it there, and then you'll have the pH really quickly. You could still use KW and take the OH minus concentration, convert it to H plus, and then go into the pH. They both should give you the same answer when it's all said and done. So we have the pH equation here. We'll add to our list. We also have our friend KW. I feel like we should add some more. Good idea. So if you are given, for example, the pH, you could get directly from that value the H plus concentration. So if you're actually given the pH value, you could calculate the H plus concentration directly from it. And the H plus concentration in that case would equal the inverse log of the negative pH. Now, in most people's calculators, when they hit the inverse log, it pops up a 10 and a caret. You want to make sure you make it negative pH. That is also how some people do scientific notation incorrectly in their calculators by using those buttons, which is why you definitely don't want to use those buttons here for scientific notation. Otherwise, things are not going to go good for you. Good news is you could do the same thing for POH. From the POH, you could get directly the OH minus concentration from it, and you could get that by pretty much the identical calculation, the inverse log of the negative POH. Once again, that usually will look like a 10 and a caret on your calculator there. How do you do the inverse log? You do the inverse log by, on most people's calculators, I would say upper left corner, there's like a second button, like a shift button happening. And usually you have a log button where there's like a 10 to the X maybe above it or something like that, or a 10 and a caret. And that's your inverse log button that you would want to use. By the way, just like everything else, if you have a display calculator, you would punch it in exactly the way it's written. You would hit the shift button or second button, and the log button to do the inverse log, you would hit the negative button and the number. If you have a non-display calculator, you would start with the number, you would then make it negative, and then you would hit shift and log. So you got to, again, work backwards if you have a non-display calculator versus a display calculator. Any questions on that there? By the way, the POH scale runs opposite of the pH scale. So the pH scale is 0, 7, 14, right? And that's acidic and basic in between. The POH is also 0, 7, and 14, but that's acidic and that's basic. They run opposites of each other because as one goes up, the other goes down. So it's opposite in terms of that. That is why I said earlier that when you're deciding acidic, basic, or neutral, this is the scale most people have in their head, and that is the number you should look at. That is also why people give you that funny answer I said earlier. They will calculate the pH and go, cool, it's above 7, it's basic. Then they'll calculate the POH and go, cool, it's below 7, it's acidic. And before you know it, you have an acidic and basic solution happening in that situation. So only one answer for that question. Always look at the pH scale because that's usually the scale most people have sort of in their head. Any questions on that? By the way, can you get a pH above 14 or a negative pH? The answer is, what happens if I have 18 molar hydrochloric acid? The H plus concentration would be 18 molar. What is minus the log of 18 molar? I don't know either. I'm just going to punch that in myself. Minus the log of 18. That looks like a negative 1.25, yeah? That's like a super strong acid, yeah? They call that super acid. And with a pH less than 0, you should be super careful with it. Hence all the warnings I gave you the other day, right? When we were playing with whatever acid that was very, very strong, yeah? So you can technically, with a really high concentrated acid, get actually a pH that's less than 0. Again, sometimes referred to as a superacid, and obviously you should be super careful with it. Yes, we usually deal with more dilute acids, right, in our work, which will sort of fall into the pH scale somewhere on there along the way. So keep that in mind as well. It is possible. Not very common, but it is possible. All right, let's try some of our calculation ways here. The pH of rainwater is 4.82. I don't care what it says. Let's do this instead. I want you to calculate the H plus, like it says, I suppose. I want you to calculate the OH minus concentration. I want you to calculate the POH. And I want you to tell me, is it acidic, basic, or neutral? And on the bottom there, we have the OH minus concentration. So for the bottom one, I want you to calculate the pH, the POH, the H plus concentration, and is it acidic, basic, or neutral? All right, so take a few moments, calculate all those things. Get your calculator out so you know how to do it with your calculator. Okay, let's take a look, see how we're doing. So in this particular case, we have the pH. So again, we have a few options. Probably the best option, or one of the easiest options, would be to calculate the POH from that. We could also do what the question asks, which is calculate directly from that the H plus concentration. So I'm going to start with the POH since I asked you to do everything. So the POH in this case would equal 14 minus the pH, and that comes from the relationship of the pH plus the POH equals 14. So if I do that, that will give me 14 minus 4.82, and that's going to get me here 14 minus 4.82. 9.18 as my POH. Now I can get my H plus concentration as well from my pH. So again, the H plus concentration will equal the inverse log of the negative pH. So again, on your calculator, when you punch that in, you probably will be looking like a 10 and a caret type of thing on your screen. Remember to make it negative 4.82, and that will get you 1.5 times 10 to the minus 5 molar in this particular case. At this point, you also have really, since of the way I did it here, two options. You could go into KW and like we did previously and solve for the OH minus concentration. You could also do the same thing with the POH that we just did with the H plus concentration or the pH to get the OH minus. So once again, I'm going to do it this way here. OH minus will equal the inverse log of the negative POH, which again, on your calculator will be a 10 and a negative 9.18. Once again, to punch that in, probably like the second button or the shift button, the log button, the negative button, and 9.18. Obviously, if you have a non-display, you got to go backwards and start with a 9.18 and punch it in sort of the opposite way. And if you do all that there, you will get negative 9.18. There it is. We'll call it 6.6 times 10 to the minus 10 molar. We do need concentration units as it is a concentration in this particular case. Once again, if you chose the KW route, you could have done OH minus is equal to 1 times 10 to the minus 14, which is KW, divided by 1.5 times 10 to the minus 5. And that will get you maybe 6.7 with some rounding there, times 10 to the minus 10, but pretty much the same answer if you wanted to go that way with it as well. So that's sort of one of the alternative ways of doing that. Is this acidic, basic, or neutral, this one? I'm going to go with, we want to look at the pH, right, which is 4.82, and that's less than 7. So this is acidic, which I think it was talking about acidic rain almost. So that would make a little sense there. Question on any of those things there. Now, a couple of things, right? We had 2 decimal places there, which means when we got to our concentration, we had 2 significant figures, right? Same thing here, 2 significant figures from our 2 decimal places as well. Any questions on any of those things there? All right, looking at the bottom one, we have the hydroxide concentration, which means, again, we have a few options as to where we could start since we're calculating everything. We could use KW again if you like to get the H plus concentration. We could also get the POH as well right off the bat by taking minus the log of our OH minus concentration. So we did both of those. See what we end up with here. 1 to the minus 14 divided by 2.5 to the minus 7. Going to get me a 4.0 times 10 to the minus 8, and we do need a concentration. We'll do minus the log of 2.5 to the minus 7. Going to give us a POH of 6.60. At this point, we can then use our pH plus our POH is equal to 14 to get our pH value. So our pH will equal 14 minus our POH, which will give us 14 minus 6.60. That'll be 14 minus 6.60. Gonna get a 7.40 in this case. And I feel like I'm missing something. Maybe I'm not missing anything. I got all of them, I think. At this point, as well, if you chose to get the pH before you did the H plus, you could take this number and again, inverse log of that to get to the H plus, if you didn't do it right off the bat with KW, so you could went that way as well. Acidic, basic, neutral, this one's going to be slightly basic. Yeah, a little bit above 7 there. Not too far to be right on 7. Yeah. So it needs to be like super close to 7, like, 7.01 or something like that, or 6.98 or something like that but maybe I'll take it for neutral. Yeah. Any questions on that there? You obviously need to be able to calculate all those things, H plus, OH minus concentration, pH, pOH, given any of these things, pH, pOH, concentrations, and stuff like that. Any questions on how to do that? I find most people struggle with, I'm not sure which way to punch it into my calculator or which formula I should use for what. So, if you have a concentration and you're looking for a pH or pOH, again, you should end up with just a number between 0 and 14, right? And if you have a number between 0 and 14, you need a concentration. Probably in a lot of cases, we'll have like an exponent, like times 10 to the something type number. All right. Let's try one more here to finish it out. Let's also add, we have the H plus given to us, which again, since we're really looking for everything, does give us two options as to, depends which way we want to go. We can, in one option, go into KW and get the OH minus concentration by taking 1 times 10 to the minus 14 and dividing it by 3.5 times 10 to the minus 6. We also have the H plus concentration, which means we could also directly calculate the pH. So we have a couple of different ways, however you want to do it. So why not, for old time's sake, we'll go into KW here first, and we will take our KW divided by our H plus will give us 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 6. And if we do that there, that's going to give us 2.9, looks like. 2.9 times 10 to the minus 9 molar. Now at this point, I'm just going to go into the pH equation, and that's going to give me pH is equal to minus the log of the H plus, which will give me minus the log of 3.5 times 10 to the minus 6, and minus log 3.5 to the negative 6, making sure using my exponent button. And that's going to give me a 5.46 pH. At this point, I can now use the pH plus the pOH relationship that's equal to 14 and get my pOH by simply subtracting the 14 from that. And that seems like a much easier move. So why don't we just do it that way? That looks like an 8.54 at this point. I think I got everything right. 1, 2, 3. And at this point, we will decide that this is acidic, basic, or neutral. This one's going to be acidic, as we want to look again here at the pH, which is 5.46 and less than 7. Any questions on that there? Questions on anything we talked about?